Anybody have any homework questions you'd like me to go over? All right. I'm just going to go through some problems, give you some problems to work on. We haven't done a ton of spring-related problems. Oh, by the way, the quiz, we're going to do that at the end of class. Okay, so let's say we have a rolling thing connected to a spring, and it doesn't make any difference which way the spring is oriented. And let's say that this thing has a mass of m and a spring constant of k. And let's say we stretch the spring, let's call it an amount L, and release it from rest. What's going to happen? Okay, so just for like an intuitive understanding, if you, if this is the spring's resting length and you pull it back to here and release it, okay, so this is the object's location. At the spring's resting length. And you pull it back to here and let it go. It's going to move. So this is the path the object is going to follow. It's going to go to the resting length, return to its resting length, overshoot that exactly to an amount L on the other side of the spring's resting length. Okay. And then it's going to keep just doing this forever, just oscillating back and forth. Okay. When the spring is at the two extremes, so here and here, whenever the object is at the two edges of the motion, instantaneously the velocity is going to be equal to 0. Okay, because it's about to turn around and go the other way. It's the same thing as if you throw an object up in the air. Okay, and then every time the spring passes through its resting length like this, it will be at its maximum speed. Whichever way it's going, that speed is going to be the same. Okay, so let me show how that works using conservation of mechanical energy. Okay. So first, let's calculate the speed of the object when x is equal to L. Okay, so what I'm saying is we're going to calculate, remember x means how much the spring is deformed from its resting length. We're going to calculate what the speed is of the object when the object is all the way that distance L on one side of the spring's resting length, like L shorter than the resting length, and when it's L longer than the resting length. And what are we going to get for those? 0, okay? So we're going to show that at those two extremes, the speed is 0. Well, first, think of a free body diagram. just to convince yourself that we can use conservation of mechanical energy. There's a weight force down, there's a normal force up, there's a spring force that way. It could be the opposite way too, but this is the weight, this is the normal force. Okay, can we deal with all of these? Yeah, gravity is a conservative force that we have a potential energy for. So that's good. This is non-conservative, which can be a problem, but the work is equal to 0. Okay? And the spring force, that's conservative. We have a potential energy function for that. So this will work fine. And now our instants are going to be at instant 1. This is when the object is released. And instant 2 is going to be when x is equal to L, okay, when we're at those two extremes. Are you with me on that? Is anyone with me on that? 2 people. That's great. That's my record so far this semester. Okay, so at instant 1, all right, well, the first thing we have to do in any motion like this is choose an h equals 0. Okay, let's choose it where the object is. I mean, this object never changes height. So if we call this h equals 0, that's going to just make the gravitational potential 0 the whole time, because we'll be multiplying a 0 to everything. So gravitational potential energy is equal to the mass times 9.81 times 0. So this is equal to 0. The spring potential energy is 1/2 times K times, when it's released, what's X equal to? How far is the spring stretched or compressed from its resting length? L, right. So this is going to be L squared. And we can't really simplify it more than that because I'm just using these constants to represent everything. And then the kinetic energy when it's released is 1/2 times the mass times what's the speed at the instant it's released? Released from rest. So the speed is 0. So 0 kinetic energy. Now we're going to calculate the speed of the thing at instant 2, when we're at either one of those two extremes. Gravitational potential energy, we're multiplying by a height of 0, so that's going to be 0. The spring potential energy is 1/2 times K times, what's X in this case? L. And the kinetic energy, we're trying to calculate this speed, so it's 1/2 times mass times speed squared. And now put it into conservation of mechanical energy. So 0 plus 1/2 KL squared plus 0 is equal to 0 plus 1/2 KL squared plus 1/2 mv squared. Subtract this from both sides, and you get 1/2 mv squared is equal to 0. So v has to be equal to 0. Okay? So what that says is anytime the spring is deformed that distance L from its resting length, the speed is 0. Okay? Now what's the speed when the mass moves through the spring's resting length, when it gets to that middle point in its motion? Okay? So what's the speed when it passes through the spring's resting length. We can use conservation of mechanical energy. The free body diagram looks the same, so I'm just going to go right to the 2 instants. Instant 1, again, that's going to be when it's released. Instant 2 is when the spring is at its resting length. So what would that x value be at that point? 0, yep. So at the instant it's released, this is all going to be the same stuff we had for instant 1 before. 0 gravitational potential energy. The spring potential energy is 1/2 times k times L squared. The kinetic energy, V, is 0 when it's released, so this is going to be 0. At instant 2, gravitational potential energy is 0. The spring potential energy is 1/2 times k times 0 squared, so 0. The kinetic energy is 1/2 times the mass times the speed squared that we're going to calculate. And so conservation of mechanical energy says that's not 1, that's 0. 0 plus 1/2 k L squared plus 0 is equal to 0 plus 0 plus 1/2 m v squared. Multiply everything by 2 and we get KL squared is equal to mv squared. Divide both sides by m and you get v squared is equal to KL squared over m. Take the square root of both sides and you get that v is equal to, we want the positive because we're looking for a speed, L times square root of k over m. This is equal to KL squared over m square root. And then square root of L squared is L, so you can pull that out and you get this. I just simplified it in 2 steps, did 2 steps in 1. And this is the fastest it ever goes. And it happens in both directions, as it's going from being compressed through that middle point or when it's going from being stretched through that middle point. Anybody have any questions about how that works? This is almost exactly what you have to do in number 5 of the homework, except that in number 5 you have numbers for these and not constants. Okay, but the approach is the same. Now I want to do a couple of problems where we're going to use conservation of mechanical energy and conservation of linear momentum both in the same problem. Okay, this is something that comes up pretty often. They go together pretty naturally. So the first one, I think some people kind of find this interesting as an application. This is called a ballistic pendulum. So if you manufacture a gun or whatever, and you're trying to figure out how fast it shoots. Now it's easy because you have really high-speed videos that can just measure the distance that it travels in some amount of time. It's really easy. But not very long ago, that wasn't available as an option. So how did people know what the muzzle speed of a bullet was? Was there any way to know? And the answer is this idea, ballistic pendulum. And the way it works is you have a mass that you know, and you fire a bullet into that mass. And as a result of that bullet hitting the mass and the bullet together swing up like this. And so there's some distance, some height that the thing travels because of that collision. Okay, so let's call this H. And if you know the mass of the hanging thing and you know the mass of the bullet, you can use conservation of linear momentum and conservation of mechanical energy to calculate how fast the bullet was going when it lodged into the mass. Okay? So the way it works is you use conservation of linear momentum for the inelastic collision. And you use conservation of mechanical energy for the swinging part. Okay? So I'm going to go through this. This is a little more complicated than problems that I'm going to give you to do, just in the way that the algebra works and how you have to carry variables around and stuff like that. But after I do this, I'm going to give you kind of a more straightforward problem that sort of uses a similar idea. Okay? All right, so the first thing we're going to do is, so the basic idea is the bullet hits the mass, sticks in the mass, and after that collision is over, that mass is swinging with some velocity. And the velocity that the mass is swinging with is way less than the velocity of the bullet because the mass of the hanging thing is so much bigger than the mass of the bullet. Okay? Now that the whole system, the bullet and the mass together, are moving with some velocity, that velocity is going to make it swing up a height h. And if you measure that height h, which is easy to measure just visually, you can't measure the speed of a bullet visually, but you can easily measure how high this thing swings. You can back calculate what the speed of the bullet was. Okay, so let's first do the collision. I'm going to think of this from above because notice that the bullet, remember that the rule for using conservation of linear momentum is the net external force on your system has to be 0. Okay? If you're thinking of it from a side view, it's not much force on the system because gravity doesn't apply a very big force to a tiny bullet, you know? But it is something, so just out of principle, I'm going to take a top view. It's not going to end up changing anything. And I'm going to say that the mass is, so I'm going to say that the mass of the hanging thing is 1 kilogram. The mass of the bullet is 0.005 kilograms. And the height that it swings up is 0.4 meters. So this is a top-down view. There's the bullet. There's the mass. And I'm going to start with a coordinate system like this. So before the collision, the mass of 0.005 has a velocity of, well, we're trying to figure out what that is, but we know it's moving in the positive x direction. So I'm going to call it capital V 0. The thing we're trying to find is that capital V. The mass of 1 kilogram has a velocity of 0. After the collision, the bullet is lodged in the mass, so we have a single thing with a mass of 1.005. And its velocity after the collision is lowercase vx, lowercase vy. We're going to calculate what those are. The x equation says 0.005 v plus 0 is equal to 1.005 vx. And so the x component of the velocity after the collision let's see. So 0.005 divided by 1.005, and we get Vx is equal to 0.00497 times capital V. Do you see how that works? And then we'll go to the y equation. That says 0 plus 0 is equal to 1.005 Vy. So Vy is equal to 0. And so all together, what we have is that the velocity of this combined system after the collision is over is equal to 0.004975 for times capital V for the x component, and 0 for the y component. So right after the collision, this thing has a speed that's, you can think of this as 0.4975% of the speed of the bullet. You know, it's moving much slower now because this very light thing collided with this very heavy thing. So now that we know that this is the speed of the whole thing, now we can use conservation of mechanical energy to see how high it swings. Okay? So now we're going to think about the swing phase. Well, we have to think about whether we can use conservation of mechanical energy for this. A free body diagram of the system. We have the mass with the bullet inside. The force of gravity is acting on it. And then the only other force acting on it is a cable force T. This we know is fine. We use weight all the time in conservation of mechanical energy. This is conservative. And we have a potential energy function for it. What about this cable force? That's non-conservative. So is that a problem? Well, it's something you need to think about, but in this case, notice that the motion that this is swinging is a circular motion, okay? And that cable force is toward the center of the circular motion. In other words, that's a non-conservative force that does zero work. Remember that the two non-conservative forces that do zero work are normal forces in rolling and sliding, and centripetal forces, forces toward the center of a circular motion. And that's what that cable force is, okay? I'm going to choose the lowest, the hanging height of this to be my h equals 0. I've said that for choosing my h equals 0, I just always choose the lowest point in any problem. So my instant 1 is going to be immediately after the collision. My instant 2 is going to be when the mass swings to its highest point. Okay, so we need a gravitational potential energy. That is the mass, which now is 1.005 because it has the bullet lodged in it, times 9.81, times the height at instant 1. What's the height? Oh, my hand wrote it before I... Yeah, 0. So the potential energy comes to 0. And then the kinetic energy, right after the collision, is 1/2 times the mass times the speed squared. Do we know what the speed is?
0.00475.
Times v.
Yeah.
So we still have that variable in, but yes, we have an expression for it. So this is going to be 0.004975 times v, and we're squaring it because that's what you do for a kinetic energy. And so let's see. That is 1 point, it's really small, 1.2437 times 10 to the minus 5th times capital V. Squared, sorry. You have to square the 0.004975 and you also have to square that V. And now we'll go to the highest point. At the highest point, the gravitational potential energy is 1.005 times 9.81 times the height is 0.4. And so we get a value of 3.944 joules. And the kinetic energy is 1/2 times the mass times v squared. What's the speed of this ball when it gets to the highest point? 0, right. It's just about to turn around and go back the way it came. And so this is 0. And now plug it into conservation of mechanical energy. We have 0 plus 1.2437 times 10 to the minus 5th times v squared is equal to 3.944 plus 0. Divide both sides by 1.2437 times 10 to the minus 5th. And you get that v squared is equal to 317,083. Take the square root of both sides. We're looking for a speed, so we want the positive one. And you get a speed of 563.10 meters per second. Anybody have any questions about that? So in problems like this, you always want to use conservation of linear momentum just for the part that's the collision. And then look for, in this case, look for conservation of mechanical energy to see if you can do the other parts with it. Okay. So now let me give you sort of a similar type of problem. And I'll give you time to do the steps. So let's say we have a hill, and then a flat section, and then another hill. And we start by pushing a 1 kilogram cart down the hill. This hill has a height of 1 meter. Down on the flat part, there's another cart with a mass of 0.5 kilogram. And so the 1 kilogram cart starts at rest. When it gets to the bottom of the hill, the two carts latch together. And we want to know how high up the hill does the pair of carts reach. Okay? So what we're going to do, in the last one, it was only 2 steps that we had to do, although we had to carry some variables around and stuff that made it sort of funky. This is going to be 3 steps. What do you think the first step is going to be? So the first thing that happens is the 1 kilogram cart rolls down the hill. What are we going to use for that calculation? Yeah, right. We're going to use conservation of mechanical energy for the roll down the hill. Once the 1 kilogram cart is rolled down the hill, what are we going to use for the collision? Yep. So conservation of linear momentum for the collision. And then once they're linked together, they're going to roll some height up this hill. What are we going to use for that? Mechanical energy, yep. For these to roll up the hill. Well, the first thing we're going to do is conservation of mechanical energy just to see how fast the 1 kilogram cart is moving at the bottom of the hill. We have to choose a height equals 0, and I'm going to choose it at the lowest thing in that problem, so I'm going to put it on the flat. Take a few minutes and see if you can calculate how fast the 1 kilogram cart is moving when it gets to the bottom of the hill. So now we're going to use conservation of mechanical energy. Instant 1 is going to be immediately after the latch. And instant 2 is going to be at the highest point up the hill. The gravitational potential energy. Now these two things, we're going to treat them as a single object with a mass of 1.5 kilograms. So this is 1.5 times 9.81 times the height right after they latch. It's on the flat, so that's 0. So we get 0 for gravitational potential energy. For the kinetic energy, we get 1/2 times the mass, 1.5, times the speed squared, so 2.95 squared. And you get about 2.18 joules. Nope. 0.75. 6.53. And then when it gets to the highest point, we have the mass, 1.5, times 9.81, times the height that we don't know yet. We're trying to calculate that, so I'll leave that as h. And then for the kinetic energy, 1/2 times 1.5. What's the speed when it reaches the highest point? 0. So times 0 squared, so that's 0 for the kinetic energy. And so conservation of mechanical energy says 0 plus 6.53 is equal to 14.715 H. And so H is equal to 0.44 meters. So this pair of things will roll 0.44 meters up the hill. And when I say, I do want to be clear about one thing. Remember that when we're using gravitational potential energy, we're always talking about the change in height. We're not talking about like a distance traveled. So I'm not saying it'll go a distance of 0.44 meters up the hill. We don't even have any information about what the hill looks like. It could be very shallow or it could be very steep, you know. But what we know is that this is going to make it a height of 0.44 meters. And since we're assuming no friction, it doesn't matter what the shape of the hill is. That's the change in height that it'll achieve. Anybody have any questions about that? Okay, so the homework assignment that I'll give you for today, it's just a single problem. It won't take that long, but it's this kind of thing, combining these two conservation laws. And let's do the quiz.